Yeah, we can start now. Okay, so today is 14th. This 14th of April 2023. We'll be solving assignments with core assignment with 10. Okay, what is this? Okay, so looks fine for me. Yeah. So, coming with the first question, with 10, it is saying that class activation maps are used for. Okay, it's asking class activation maps. Class activation maps or CAM. So I'll start by saying what is class activation maps. Okay, so if you see any region proposal network, region proposal or object localization, let me rename that object localization algorithm. What it does, so what it does is that it takes an image. Okay, so there is some boy and holding a dog sort of thing, and it passes it to normal CNN. So CNN one, this is CNN two, this is CNN three, and so on. So as you know, when you pass certain image into CNN, what happens is that, so this is the image. Let's say there are three channels. Okay, red, green, and blue. What happens is that the number of channels keeps on increasing, and the width and height of the image keeps on decreasing. So the image will be smaller, but the height and width of the image, but the number of channels will increase with the layers. Okay, so after some layers, it will come such that okay, okay, so after some point, it will come such that the will be channel will be very low. Let me choose a different one like this. Okay, the channel will be very low. After a while, the size of image will be very low, but the number of channel will increase too much, and it will be increased so much such that so the this entire image is represented using this just small portion of the uh, small person. Okay, and it is safe to say that each channel. So now each channel has sort of each channel is sort of capturing one thing out of image. Not all. Each channel sort of capturing one thing out of the image, and when you so what they do is that they do a max pull. They do a max pull. Uh, they do a max pull on each channel. On each channel. So a max pull on each channel. So if the number of channel here is let's see, okay. So I'll get a max pull this channel wise max pull this. I'll get C values, and each values will have a maximum value in the channel. Then I will connect this. Suppose there are k classes. I will connect this to k classes to classify what this exact thing is. Okay, and after doing that, I'll be getting. Let me complete this. So after doing that, I'll be getting corresponding score. Suppose there is a neuron for dog, and here is a neuron for boy. I'll be getting that particular output activated for my task. So the thing is that now each layer here, each channel here represent one object, and if we just take a max pull and put it on a classification channel, we'll get the classification score for uh, each and every um, class or object present in the image. Let me fix. So how do I standard? Yeah. So this is the view we'll be uh, capturing. Okay, so this is the thing, and if you see the question, class activation maps are used for. So this is the class of activation. This is the class activation. The question is the class activation map are used for the accurate definition of object boundaries, pixel level leveling of semantic segmentation. Okay, option B is not correct because this is not semantic segmentation. This is object localization. Option B is not correct. Option C is improving prediction accuracy of CNNs and a classification task. Option C is not correct because this is not a classification task. First, the accurate delimitation of object boundaries. No, we're not doing the exact accurate delineation of object boundaries. Suppose here is apple. Okay, so we're not going to draw a boundary around it in our algorithm. In the reason proposal, what we do is that we just propose a reason around it, like suppose something like this. We'll propose something like this. Okay, so apple is here present here. So this is the correct uh, task uh, that we are doing. So hence the option is option D. Okay. Then come to the question number 2. What is the purpose of region-based convolution neural network RCNN? Okay. So object detection. So question number 2. Question number 2. Question number 2. In the question number 2, it is asking that what is the purpose of region-based convolution neural networks? So RCNN basically. RCN. Okay. So if you don't know RCN, I'll just discuss it for a bit. So RCNN is that reason-based CNN. So what happens is that given an image, suppose an image is given, so there might be different reasons in the image. So what RCNN is that it proposes, so given an image, there might be different object in an image. So let me just draw one image for your reference. So suppose let's say here is a boy. The boy, and here is a table, and here are some glasses, and here is a jug of water, and let's say here is a bookshelf with book. Okay, this is a mess. So there are like 4 5 objects present in this image. One is the boy, one is the book, one is glasses, one is this jug, and one is this table. So to detect object in an image, so what is the trivial way? The trivial way is that you just, so what is the trivial way of detecting an object in the image? So trivial way is first is find the reason where the object lies. Okay. Second is uh, classify the object in that region. Basically, this is image classification. And this is reason finding. Okay. Yes. Okay. Okay. So finding the reason where the object lies. So how do I find a reason where my object, where all the object is lying? So coming to the goal one, finding the reason. So one way is that you find find all the possible reasons. Okay, find all the possible reasons. Second is find selected reasons. Okay, so finding all the possible reason is not that feasible, because let's say the image is of size uh, 80 cross 80. If I go on and start finding all the can I lock this? Okay, is it locked now? Yes. Okay. If I find 80 cross 80, it is, I can find region of 1 plus 1, can find region of 2 plus 2, can find region of 3 cross 3, and so on. So it will be it will be interactable to find all the possible regions and start drawing boxes and sort of detecting uh, uh, objects around it. But if I what I can do is that I can sort of find selected reasons around images. So that's why we use reason, proposal, network. So what a reason proposal network do is that it will take an image as an input, in the output it will give proposals of proposal of reasons using one numbers where the network thinks an object might present. So coming back to this picture, this picture takes in images, and now it proposed that okay, this might be an object, 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 this might be an object. There might be some wrong proposals as well. Like it might say that okay, might be an object, or this might be an object, or head is another object, or this is another object, this is another object, like that. But we'll take all the regions, and we have also schemes to reject that okay, this reason cannot be a proper reason. So we have also schemes for that as well. So one scheme is that suppose he is a face and he's a man. Okay, so one is saying that this is one reason, another is saying that this is one reason. Okay, here we can say that the man. So here is saying that it is a face, of- and here it is saying that it is a body or it is a human. Okay, so the thing is that if we consider both the things, then it is a waste of time, right? Like we just are doing the same thing. We just subset of the body. What we do is that we see how much one box is another inside another. So, so this like is called intersection over union. So how much it is intersected and how much is the total. So here now is the total area. This is let's say 40 and this is 10. Intersection is 10. Union is 40. Okay. So this is 1/4. Yeah, I don't think this is the metric to use, but yeah, what happens is that we do we do we do see like how much we're getting an extra. Like if two boxes are like this, then it is ideal to consider these are two different boxes. If two boxes are like this, or this, is it is safe to say that these both are representing the same thing. Okay, so yeah, so it is this thing. Yeah, so this is like some basics of region proposal network. So once this region proposal network gives out regions, what we do is that we take those regions. Okay, suppose these are different regions, and we pass a CNN, then a FC, a classifier, CNN, FC, CNN, FC, and so on. Basically, classify it as something. Okay, so these regions will be passed into CNN and fully connected layer to get classified by some classification algorithm in architecture. So the answer to the question number two is what is the purpose of region-based convolution neural network? To generate a new generate video by using multiple images, no, to detect and classify objects within an image. Yes. to detect objects. Okay, nice. Question number 3. Let me choose a different color. Done. Question 3. If WCK, let me write. If WCK denote the weight of neuron corresponding to the seed class in the classification layer for the kth input feature channel FK, then the class activation map MCXY at the pixel location XY for seed class can be computed as uh, okay, so it is saying that so this is the input feature channel. This is the input feature channel, and we took max pull out of it. Got this, okay, and we have the output layer. Okay, we're saying that WCK is the weight of neuron correspond to seed class in the activation layer and kth input feature vector feature channel FK. So let's say this is FK, this will be FK, this will be FK, and this is, let's say this is class C. Let's say this is WKC. Okay. The question is, then the class activation map MC XY at pixel location XY. Map MC XY pixel location XY for the seed class. Pixel location XY XY XY. Then the class activation map MC at the pixel location XY for the seed class. For the seed class can be computed as so yeah, so see, I mean, a class activation map MC at pixel location XY for the seed class. Okay, so this FK is sort of feature that you're getting from the input. So this is coming long back from the input image where we have this X and Y. So if I put FK, if I put FK XY, so I'll get this one. Okay. For X and Y, for any X and Y, if I pass it to through this network and FK function, which is null, I'll get FK XY. Okay. And if I multiply this thing, if I mark it like this, okay. And if I multiply this with WKC, okay, I'll be getting, it will be equal to FK XY times WKC. Okay, so the thing is that So this is the output that we are getting per C from the catch channel. Okay. So what I will be getting if I do it for the entire K, for each K. So there will be summation. There will be a summation. So for each K, for each K, I will take, so for each K, like for each of the things, what I will do, I'll take FK, X and Y, then I'll multiply this with WKC. So what we're doing, the target, target words are these words. Okay. So to get all these features can be obtained using this. Okay, and the features can be obtained using this. WC is corresponding WCs will be WCK. So this will give me AC, or I can say OC, the class activation map for our problem. So the answer will be A. Yeah. Then we go to question number 4. Question number Question number 4. The question number 3 is clear, I guess. Question number 4. Question number 4. Let me take a pause for that. Coming to question number 4. Question number 4 is intersection over union, also called the Jacquard index, is commonly used to evaluate the performance of object detection and semantic segmentation tasks. Object detection and semantic segmentation tasks. If TP equal to true positive, TN equal to true negative, FP is equal to false positive, and Fn equals to false negative at a pixel level, then IOU is defined as, okay, and it is bounded in the range of. So the range I will tell, okay. So mm, uh, let me check some over event. Hmm. Uh, so yeah, so let's say there is uh, hmm, hmm, yeah. What happens is that let's say we have, okay, so here it is telling that let's say I have four values, okay, uh, three values, so true, four values, true positive, true negative, false positive, and false and false negative. I have four values. So let me first say what an intersection over union means. Okay, suppose here is a cat. You can draw it in black. There's a cat. Done. Suppose there is a cat. Okay, I'm just sitting here. So the actual boundary around it is like this. Okay, and let let's assume that your object detection algorithm predicted a boundary like this. Okay, so if we closely see the two box, one is like this, and another one is sorry, like this. So how do I evaluate how good our box or prediction are? How do I evaluate? So one metric is IOU. So IOU is a metric. What it does is that what it does is that suppose this is mm, copy just so let me so this is the area of intersection, and this is the area, this is the area of union. So what this metric does is that it asks to bring the intersection area over the union area. Okay, so equal to this equals to intersection over union. Simple. So so what does it mean that? So if I'm trying to evaluate any of the detection algorithm, uh, it will be better. So as this kind of, so what is the maximum intersection that I can get? Minimum intersection. The minimum intersection is 0. So uh, minimum intersection. Minimum intersection can be 0. How? Like if I have an image like this, and another thing. So let's say my bounding works actually is like this, but the predicted bounding works is like this. So intersection is 0 in this case. So what is the maximum intersection that I can get? Max intersection. It can be like anything. So let's say it can be the entire area. The entire area A. In this case, it will be like if the actual box is like this. Predicted is also like this. Okay. So predicted is also like this, and the predicted is same as the actual. Okay. This is the minimum intersection, maximum intersection. So what is the minimum union? It is the minimum union. The minimum union is like just very small value. Let's say alpha, because let's say it can be okay. So minimum union is okay. Let's the area of first image is, let's say, A1. Second area is A2. Maximum intersection is I would say, let me erase this one. So maximum intersection can be said as intersection, right? Intersection would be okay. No, yeah. So we are looking for this one. Okay, the maximum intersection would be the minimum of A1 and A2, right? What is the minimum? What is the max minimum union? The minimum union would be if they overlap. Minimum union would be if they overlap like this. It would be maximum of A1 and A2. Coming to the final one, what is the maximum intersection? Maximum intersection is would be, let me erase this alpha as well. Maximum intersection would be if sorry, this is maximum union. Maximum union. Maximum union would be like this. They are not connected at all. So it will be A1 plus A2. Okay. So what is the minimum value that I can get out of this? So if my so in the denominator there is never zero. There will always be something, because the union is ranging from A1 or A2 to A1 plus A2. Okay. So we are, in the denominator we have union. So intersection. This is intersection, and this is my union. So in the denominator I have always in the union I have always some positive number. In that in the numerator I have sort of minimum value is sort of say 0. Okay. So minimum value will be 0 by any positive number will be 0. So you're sort of finding the range of IOV metric. Then there is maximum. Okay. when you're going to maximum, the thing is that uh, what is the maximum thing that I can get? Okay, so for the maximum thing, I need to go for the maximum. I need to go for the maximum thing that I can achieve in the denominator, and the minimum thing that I can achieve in the numerator. The maximum thing that I can achieve in the numerator is minimum of A1 and A2. Minimum of A1 and A2, and the minimum thing that I can get in the numerator uh, is maximum of A1 and A2. A1 and A2. So as a worst case, sort of, what is the worst case that I can get? The worst case is that this both will be same. If they is same, they will be equals to 1. Because if something is, so suppose say A1 is, suppose let's just dissect this, let this A1 is greater than A2. Okay. The top will be, if the A1 is greater than A2, the top part will be minimum of A1 and A2, will be A1 and will be A2. Okay. This will be A2. Here A1 is greater than, okay, A1 is greater than A2. So that means A1 is greater than A2, the minimum will be A2, A2, and here maximum will be A1. So this will be a fraction because A2 is less than A1. The opposite happens, like A1 less than A2, then it will be A2 by A1. It's a fraction, and it will also be a fraction if A1 equals to A2, A1 by, so A1 by A1 equals to 1. The range of this is, okay, so the range of this is stuck somehow, I don't know. Okay, the range is 0 to 1. The formula is this one, intersection over union. But it acts as to represent it as true positive, true negative, false positive, or false negative. So, if I just restructure my, the diagram that I did, it will come as true positive. Like was the part we got positive, and by everything else, so it will be like true positive by false negative plus true positive plus false positive. Okay, yeah. So this is the case. Hmm. Okay. So then coming to question number 5. Which of the following is true for semantic segmentation? It's a very simple question. Not spend much of time here. Question 5. Question 5. The question 5 says, which of the following is true for semantic segmentation? So before starting, I'll just give a brief idea about what is semantic segmentation. What is semantics? Okay. So semantics is that semantic is that suppose here's a road, okay, and there are some trees. Here's a car, let's say. Good. Now here's a house. So what semantic segmentation will do is that to segment this as yellow, segment this as sky, segment this as sky. Okay. Sky and segment this as black, and let's say segment this as red, sky as red. Okay. And let's set is segment this as green. And add something for which color should I put on the house? Yellow. So these are the segmentation that I'm getting for this. Yes, okay. So what semantic segmentation do is that it just semantically segment these images into various regions. Semantic segmentation. Okay. Okay. So which of the following is true for semantic segmentation? Semantic segmentation can be considered as pixel-wise classification problem. So if we see, we're not classifying the entire image, or even if we're not detecting objects out of it, what we're doing is that we are sort of okay. Mhm. What did you say that? Okay, so what did you do? That took this part and classify this as something else. So let me pick it. Okay. Nope. Nope. This I'll try. Okay, so take a picture and classify. Also here it is classifying to something as yellow. No, it is not working properly. Classifying as yellow. Okay. So Yes, it is a pixel-wise classification problem. Then coming to the option B, it has an application in autonomous driving, industrial inspection, medical image processing, etc. Option 2 is also correct. Like if this car is going, it's an autonomous driving car, and it would want the images to be segmented accordingly. So option D is also correct. So the correct answer will be option C, both are. Coming to the next question. Question number 6. Question number 6. Consider unit and segment architecture which have been modified to have same depth and number of convolution in each layer. So in terms of GPU memory requirement, unit will consume less memory due to skip connections. So unit will consume less memory to skip connections between the corresponding encoder and decoder blocks. Both the network will occupy the same amount of GPU memory. Segment will consume less memory as it stores only the max pooling indices instead of the copying the floating point encoder features. Unit will consume less GPU memory as it doesn't require to store the max pooling indices. So before starting that, I'll give a start intro on unit. So unit is like it is like this because the convolution and deconvolution is designed in such a way that it looks like you. Okay, that's what it is. But the segment is consume less memory because it stores only max pooling indices instead of the copying the floating point encoder feature. So in the encoder, when this part is encoder, and this part is decoder. Okay. This segment, what it does is that instead of storing this in values, so it store only max pool values in the floating point. So that's why the memory consumption is very less. This is a simple question. Coming to the next question, RCNN can use various CNN architecture, AlexNet, ResNet as a classifier only. So coming to question number 7. Question number 7. RCNN can use various CNN architecture, AlexNet, ResNet. So RCNN, as I mentioned earlier, RCNN. What RCNN does, RCNN what does is that takes an image, it find out reasons in the image, then it classify the object that is there in the image, classify the object that is there in the region. Okay. So what it is saying is that RCNN can use various CNN architectures such as AlexNet or ResNet or VGGNet uh, for classification classifier only, observer detector only, feature extractor only. So what they do is that they extract these features. So these networks extract the feature out of image and later it gets classified using a FC. FC. Yes, so these are only used for feature extractor. So the answer will be feature extractor only. Option C. In a semantic segmentation, yeah, in a semantic uh, in a semantic segmentation, image of size 512, 512 is divided into non-overlapping patches of 64 to 64. How many patches would be there? Okay. Question number 8. Question 8. The question 8, it is telling that semantic segmentation, the input image size is a 512 plus 512. Okay, so let me say like an image is of 6 cross 6 and I have a patch of size 2 cross 2. These are non-overlapping. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I have 36 plus 6 or 6. So let me do a patch of 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. So what I'm doing is that I'm dividing 6 by 2, 3, 6 by 2, 3, and then I'm multiplying this 9. Okay. So I'm getting this number. So I guess this will also be the case here. So let me just do that. The input size is given 512 plus 512. The patch size is given 64 plus 64. Okay. So if this is the case, let me divide 512 by 64 to the 2 to the power 9 to the 2 to the power. 32 is 4 is 16, 5 is 32, 6, 2 to the power 6 equals to 2 to the power 3. Similarly, for the breadth, I will get to the 9 by 2 to the 6, 2 to the 3. I will multiply 2 to the 3, 2 to the 3, I will get 2 to the 6, which is 64. So the option would be D. D. Option would be D. 64. Coming to question number 9. If 6 anchor boxes are used in faster SNN and the input to region proposal network is a feature map of spatial dimension 38 plus 56. If 6 anchor boxes are used in faster SNN, input to the region proposal network is a feature map of spatial dimension 38 plus 56, then the output of the region proposal network would be the region proposal network is a feature map of spatial dimension 38 plus. The region proposal network. So I guess I'm not sure how to calculate this. I'll let you know in the next class. Feature my perspective, this and the output of region proposal network. Okay, I'll let you know in the next class. Coming to the question number 10. What kind of classifier is used at output of the faster sender network within the region of the network? Uh, it will be question answer the option number D. Multi-class classification correspond to each object type. Uh, in the faster SNN, in the faster SNN, what we do is that we do some result proposal in the first. This is question number 10. We do some result proposal, and then we do some classification. So in the first layer, in the output of the faster SN network and within the region provision network, in the output we get multi-class classification. And in the result proposal, we got around, we get this binary foreground versus background classification. Okay, so this concludes week 10's question. I guess, okay, week 10's questions. We'll next move to week 11's content. Before that, we can, I guess, run the codes for those weeks. Let me see if I have a notebook or not. Let me see what is there. Not to host. Let me see what code files that I have got here. Am I recording the screen? Yeah, it's getting recorded. It's good. Okay. Let me see. Okay, so we can start running the notebook from AlexNet actually, and see how it is turning out. Okay. I'm sharing the screen. Let me start running the code for some time, and we can then go for I hope it is video. Break till 5:30. So this is a higher bound that I feel like I might come early. So yeah, let's see. Let's run some codes. So we'll be running some codes now. Let's just start with lecture number 33 and run this LexNet code. We've loaded all the things. There's error. Terminal connection. Let me expose the ports and all. Where is this code to export? Hello. Control R. Export. This one. And HTTPS proxy is also some sort of exposing this. I guess this will work now. I guess this will work now. Okay, connection failed 3 to move temporarily. What is this error? Let me find a route. Watch. City. Um, so let me find the directory. Okay, this is directory. I have already have this cipher 10. So let me use that as well. Okay. I hope it will find. Yeah. Then we'll print the dataset. Train set has 50,000 dataset and test set has 10,000 datasets. Okay. So let's just define the network, AlexNet. So we sort of created AlexNet or something. Okay. Yeah. So we're using Torch Vision. So Torch Vision is a vision library where we have a lot of pre-trained models. So one of them is AlexNet. So we're sort of using AlexNet and we're printing it. Okay. my structure and all. We printed that. Then we're counting the number of trainable parameters. Okay. So total number of trainable parameters is 61 million, which is a lot. We copied the weights as we always do. Check the availability of GPU. Oh, the CUDA is not available. I think it should be. It should be, I guess, because NVIDIA SMI. Oh, not sure what happened, but the GPU was there. Then defining loss function on optimizer. The NLL loss, which is the classic loss for classification, we're using that, and then training the network. Cannot import. A progress cannot be found. So let me see what happened here. Uh, Let me reload my notebook. So it is getting late because of these things. The time is not defined. Let me just rerun it again. Everything. Okay, iProgress is not found. I'm not sure what the error is here. iProgress is not found. Hmm. I'm not sure what is happening now, but it should be running. Uh, IPy widgets. Um, Path intelligence, Jupyter, uninstall. Let me uninstall and install it again. Let's see. Oh, not found. Hmm. We can do one thing. We can just remove the TQDM. So if it is causing TQDM, okay, and just put it as TQDM. Module is not callable. Okay, let's do from TQDM import DM. Okay. Now I guess the training will start. Yeah, the training has started, but it's not printing anything. I'm not sure why is that. It should be printing something. Jupyter notebook renderer is there. I'm also reinstalling it again, but I'm not sure why it is not doing the printing. too much time to train. I'm not sure it will be completed today or not. I guess it is trend now. Maybe, yeah, it is trend. Oh no, it's still going on. I'll make sure to find a GPU for it the next time. Okay, I guess it won't get trend soon. So I'll just stop it. And the next part that we are supposed to discuss is okay, so this is week 10's assignment. In the next final week, there will be a 3 hour session where we will discuss week 11 and week 12 assignments. And I guess this will conclude this course. And since there are no doubts that I'm getting, I'm about to first ask a question. For April. Mm, this discussion for me is the fine, and Let me see about something about the announcements. Uh, yeah, week 11 assignment solution has been released. So we'll discuss the week 11 solution in the next class, where we'll discuss these things like autoencoders and adversarial autoencoders and all these things. Then we'll discuss the questions related to that. Then we'll go to week 12, where we'll do video analytics and spatiotemporal deep learning for video analysis, active recognition, and all those things. And we'll do the week 12 assignment as well, and discuss the week 12 assignment solution as well. The thing is that this is the final 11th week, and in the next week, we'll be having a session of 3 hours from 4 to 7, I guess. And in that session, I'll try to cover week 11 and week 12 assignment. And as far as the code, you guys find a way to run this code because it is taking a lot of time. And I had a GPU in this system, but it is not currently detecting this GPU. That's why it is getting uh, taking a lot of time to run this code. Like I was saying, like I've been training this kind of from like for 15 minutes, and it's still it is training. So I guess this is the case, and I will not be running any code going forward in this course. So I have ran all these codes, and I just have to run all these codes. Actually, there is not much of a code in the later part of the course. So I guess it will be okay for you to do these things. And meanwhile, I will discuss the week 11 and week 12 content in the next week. All the best for your exams. I guess exam would be on. Uh, I guess exam would be on some. Uh, I'm not sure like when the exam is, but all the best for the exam. Yeah. So it's almost 6. We'll stop now. I'll stop the meeting, and I will upload the corresponding video to the YouTube. Thank you.